All right, now that we know what a hydrated compound is, how it forms, and we know how to name and write those formulas, the next step is to understand how to determine the formula of a hydrate from data that is provided for you or data that you would have yourselves collected in lab. So there's a couple of quick little steps here for the most basic version, and that is what this video will cover. I'll post one more video that shows how to do a little bit more of an advanced version, and that's where it gets a little bit, more challenging, just like chemistry should be. Number one, the very first step that we're going to do is to determine the mass of water that has left the compound after you've heated it. So in a laboratory setting, you would take a known mass of the hydrated compound, and then you would place that on a watch glass, set that up over a Bunsen burner, and you would gently heat and reheat and reheat until you were confident that the water had all been released from the molecule. And then you would subtract those, the starting mass from the ending mass. The ending compound, the one that has changed its color, the one that has lost the water, is called the anhydrous salt, so the salt that does not have water. So it's pretty simple math. We're just going to take the starting mass minus the anhydrous mass, and that gives us how much water was in the original compound. The next thing that we'll do is to convert the mass of the anhydrous compound, what was left over, we'll convert that over to moles by dividing by the molar mass of the ionic part of the compound. And then we'll also convert the mass of water to moles, again, by dividing the mass that was lost due to the water by the molar mass of water itself. Once we have that, we're just looking at the ratio, how many water molecules are in this compound compared to the ionic compound. So to do that, the simplest thing is to just divide the moles of water that we calculated by the moles of the anhydrous compound. We might have to round just a tiny little bit, and then we'll just write the formula. If we end up having to round a ton, it means that there was probably something wrong in the data, or the data that we collected, we didn't get all of the water out. So that's something that I'm really missing about class right now, is that opportunity for you guys to learn the concepts on paper, but then to experience it in lab. Obviously, there's going to be all sorts of factors that play out in a lab where we might not get perfect data, and that opportunity for you guys to kind of problem solve through that is what we're missing right now. So I'm kind of bummed for you guys about that. All right, but going back to this particular video, and the purpose is just to be able to do this stuff on paper and make these predictions. So here's a very classic example of how a problem like this would be worded. A 15.67 gram sample of a hydrate of magnesium carbonate was heated without decomposing the carbonate to drive off the water. Now we know that that's really hard to do, right? Carbonates themselves are really easy to break apart. And so when you're heating up a carbonate-based compound that is hydrated, you have to do it very, very gently to discourage the magnesium carbonate from breaking down into like a magnesium oxide and a carbon dioxide. So oftentimes in labs that involve carbonate compounds, our data is skewed because not only will we dehydrate the compound and we'll lose water, we'll also unknowingly break down the carbonate compound itself, and additional mass will be lost due to carbon dioxide, and that will skew our results in the end. So we have to be very, very careful in lab when we're working with carbonate-based compounds. All right, going back to this problem, the mass was found to be reduced to 7.58 grams, and what is the formula of the hydrate? So here's where we're gonna jump in and do a little bit of math. So the first thing we need to do is to determine how much water was lost. So we'll just take 15.67 minus 7.58. Everything I do in this video, I'm going to plug that into my calculator because I have been messing up calculations a bit lately due to just being too distracted in my own head. So I apologize, and I'm doing some very simple math on the calculator, but I want to make sure my numbers are accurate for you. So the difference there is 8.09. I'm going to label that right away. That is grams of water. That's how much water was actually lost. This 7.58 is going to be really important also. That's my grams of magnesium carbonate. So really important to kind of keep those things separated out. So that step one is just to determine how many grams you have of each. Step two, let me just label this really quick. So step two is to determine the number of moles of the anhydrous compound. So we have 7.58 grams of magnesium carbonate. And prior to doing this, starting this video, I just did a really quick calculation of what the molar mass of magnesium carbonate was. So I'll set that up here. It was 84.32 per 1 mole. And then I will get 7.58 divided by 84.32. I get 0.0898956. We don't have to really write out that many, but again, I'm going to label that so that I know what compound I was working with, which becomes important when I'm busy, and I start doing things too quickly. All right, step 3 was to determine how many moles of water. So we had previously calculated 8.09 grams of water. And we know, based on lots of work already with water, that the molar mass of water is 18.02 grams. So doing that math, I get 0.44894, I'll say 6 moles of water. Now, if you're doing this correctly, there always should be, if not the same number of moles of water, you know, if the compound's a 1-to-1 ratio, there should always be more moles of water, because there's always going to be more moles of water attached to one compound of the ion. So then last kind of major step that we have to do, or the last step involving math then, is just to take the moles of water and divide by the moles of the carbonate. So I'm going to just do that briefly here by dragging it down. I'm going to go ahead and divide those two and get what our answer is here. One of the reasons why I like plugging in my water second is because I know that's always going to be the greater number of moles. I have that in my calculator, so then the only number I have to actually go in and plug into the calculator was that original mole of the carbonate itself. So this rounds out to be like 4.994077, which I'm going to round to a whole number, so that gives me 5. Step 5 then was just to record the answer, you know, what is the name of this compound? So I'll sneak that in at the bottom. This compound's formula is MgCO3, and there's 5 waters, so that's the first part of this. The second part is to write the actual name of that, so that would be magnesium carbonate pentahydrate would be my final answer on that. I'm going to run out of room. That's okay. You get the point. Okay. What's really nice about problems like the ones we're going over in this example is that you're given the actual name of the compound without without indicating how many waters there are, because that's the whole point of the problem. But they're telling you what it is. In more advanced versions of this, they'll actually give you like the percent composition of every element and water in the compound, and then you have to figure that out first before you can actually figure out the answer. So we'll go over that in the next video. All right, one last practice problem. What I strongly encourage you to do at this point is to pause the video. Work this problem out yourself, and then come back to the video to see the explanation and answer. And again, if you want to, pause it here and then just fast forward it to the very end and see if your answer was correct. So again, I'm going to just walk through these steps. The first steps being to subtract. So we're going to take 4.31 minus 3.22, and that is going to give us the how much water was lost. So that's 1.09 grams of water. My anhydrous mass is always going to be that second thing, right? What I had subtracted. So I'm going to go ahead and take 3.22. I'm going to divide it by the molar mass of sodium carbonate, which I found earlier to be 105.99. That's going to give me the moles of sodium carbonate. and that's 0.03038. That's moles of Na2CO3. The next part I want to do is moles of water, so 1.09 divided by 18.02. And I get 0.06048 moles of water. Hopefully you can see that that should work out to be a 1:2 ratio. It rounds out to being 1.99105, so we're going to round that to 2 when we divide those two by each other. So 0.060488 divided by 0.030380 is going to be close enough to 2 that we'll write that down. And then the formula for this would be Na2CO3 with 2 waters attached. And then the formula name for that would be sodium carbonate dihydrate. Again, in a problem like this, one of the things that we would want to be paying attention to if we were actually going to do this in the lab setting is we just want to pay attention to the fact that we're working with a carbonate compound. We know that carbonate compounds naturally decompose under when heated, and so we'd have to be very, very, very careful not to overheat this compound or to heat it too strongly too quickly. Otherwise, our data would be really skewed and we would be getting numbers significantly greater than 2. It would make it appear as though there were a lot more water attached to these compounds than are truly attached. All right, I would encourage you at this point to stop and do the next set of problems on the homework assignment, again, which are going to look very similar to what we just covered before you move on to the what I would consider to be slightly more advanced problems.